Okay, let's start on chapter 3 on the exponential and the logarithm functions. Exponential and logarithmic functions. And they go hand in hand, right? Because exponential function and logarithm function, they are inverse functions. All right, so section 3.1 is on the exponential function and graphs. We're also going to take a look at some of the applications. First of all, let's learn how to recognize, evaluate exponential functions with base a. So here a is greater than 0, right? And a cannot be 1. Okay. And we're going to learn how to graph exponential functions and use it to use the one-to-one properties. And we're also going to learn how to recognize, evaluate, graph exponential function with base e. And the last thing is use exponential function to model and solve the real-life problems, typically in a compounding interest questions. Okay, so now first of all, let's look at the exponential function. So typical exponential function look like this: a to the x. Right? And then here a is a base. A is what we call a base. A is greater than 0 and a cannot be 1. When a equal to 1, if a equal to 1 here, then f of x will become 1 to the x, and it becomes 1 basically. So this is not an exponential function anymore because this is what we call a constant function. f of x equal to 1 is a constant function. All right, now let's take a look at some definition of the exponential function. Okay. Exponential function f of base a is denoted by this. Here a must be greater than 0, a cannot be 1, and x is always any real numbers. Right now, a is 1, I already explained it. F of x equal to 1, then it's a constant function. Okay. And typically, you know, 4 cubed equal to 64. 4 raised to half equal to 2. 4 to the half is same thing as square root of 4, right? Square root of 4 equal to 2. Okay. And let's say if 4 they raised to negative half, what do we get? First of all, we're gonna turn the 4 as a reciprocal, 1 over 4, and to the half. Again, we turn back to radicals, so it becomes square root of a quarter. And square root of quarter is radical. Square root of 1 is 1. Square root of 4 is 2, so it's half. And yeah, so that's basically, if you want to get 4 raised to any power, that's how you do it. Especially negative powers, usually it's slightly more difficult to tackle. So yeah. A raised to radical 2. Radical 2 is approximately equal to 1.41421356. So basically we use this idea, you know, moving this number as close as possible to this to estimate the answer for a to raised to radical 2. Yep, so here, if you want to find out what is the given value, the y value for given x value, let's say x equal to negative 3.1, so it's 2 raised to negative 3.1. And typically you put into the calculator, and the calculator will give you approximate answer. For the first one, 2 raised to negative 3.1 turned out to be approximately 1166. Yes. And 2 raised to negative pi power. Replace x with the pi. 2 raised to negative pi power. It's 0.1133. Yeah. And 0.6, the last one is 0.6 raised to 3 over 2, 1.5 power. Let's see what that is. 0.6 raised to 0.464748, 0.4648. Alright, so on the next slide, you can look into that in details. We'll show you how to get the exact answers, including the calculator input, right? So you can try in your own calculator right here. Use your put into the calculator and then get a result. All right, basically just substitution problem. You plug in the x values and then get a y value out of it. Okay. And now let's take a look at the graph of the exponential function. So for exponential function, we have two types of graph. F of x is equal to ax. When the base a is greater than 1, then your graph will look like this. This is the typical shape of the graph, and then it's typically called exponential growth model. Because from left to right, the graph is increasing, right? It's increasing all the way. Similarly, for the other typical case, when a is greater than 0 but less than 1, and your graph will look like this. And then this is what they call the exponential decay model. Exponential growth model used to predict population growth. Also, it's heavily applied in finance, compounding interest, right? That's another area. And for exponential decay model, famous one is in physics. In physics, that's a decay of the nuclear elements, right? Decay of nuclear elements. Those are the famous applications, but we'll get to detail later on, right? So on the same coordinate plane, sketch the graph of each function. So I have two functions, a f of x equal to 2 to the x. So in order to sketch a graph, we need all the pairs. And typically 5 order pair is okay. And right here, in the middle, I'm putting 0 right here. Okay, change it to a different color. Start with 0 in the middle. So -1, -2 goes on top, right? And then 1, 2 after that. So if you look at it, this is a sequential order. Now if you look at it, let's find the y values. F of -2 should be -2 raised to -2 every second power. If you do it algebraically, this should be half to the second. In order to cancel this negative sign, we change the number, change the base to reciprocal. Half to the second power is a quarter. Okay, a quarter is 0.25, right? So that's good. Now f of -1 should be 2 raised to -1st power. So similarly, it will become half to the 1st power. Any number raised to 1 power to the power of 1 remain as it is, because that's half. And if you look at it, there's a pattern here, right? From the previous one to next one, from quarter to half, it's twice as much. That means this base plays an important role. So without calculation, we should know that next number should be 1, because twice of half is 1. Twice of 1 is 2, right? Twice of 2 is 4. Okay, but you can easily verify this using a calculation here. So 2 to the 0 becomes 1, right? F of 1 is 2 to the first, that's 2. F of 2, 2 to the second, that's 4. So this growth model comes from the base. When the base is bigger than 1, here the base A is bigger than 1, we know it's a growth model, meaning the y value will get bigger and bigger. But every time when x value is in the sequential orders, the next y value is always twice as much as the previous y value. All right. So now if you have all of these order pairs, then you'll be able to sketch the graph. Can we just really quickly sketch right here? Look at all these x values, right? So we just need up to -2. That's enough. Same thing on the positive side, 1, 2. That's enough. Y values, the maximum is 4. So 1, 2, 3, 4. That's enough. And now let's start plotting all the pairs. -2, a quarter. This is a half. Another half, that becomes a quarter. So this is a quarter right here. And the points goes here. Let me use a different color to identify different points right here. So this first order pair, second order pair, half. So this is half. Half. It's right here. And then 0, 1 right here. 1, 2, and 2, 4. And then once you connect all these order pairs with a smooth curve, and then also this x-axis is what we call the horizontal asymptote. Because no matter what x value you pick, this 2 to the x is always greater than 0. So y value equal to 0 becomes horizontal asymptote, right? It's like the number, you know, this 2 to the x moves really closer but never touches it. That's what we call the asymptote. This is horizontal asymptote right here. Also, look at that, it passed through 0, 1, right? 0, 1 is right here. And from left to right, it's increasing, right? And next one is g of x equal 4 to the x. Similarly, we come up with order pairs. Similarly, 5 order pairs, just like the other one. So 0 in the middle, -1, -2, and then 1, 2. Okay. So in order to find the y value, and g of -2 is 4 raised to -2nd power. Similarly, it's a quarter to the 2nd power. Quarter to the 2nd is 1/16. So this is 1/16. And based on the same idea, since the base is 4, right? Base A is 4. Means next number should be, next y value should be 4 times as much. So next number should be a quarter. 4 times 1/16 should be a quarter, but let's double check. 4 raised to -1st power is a quarter to the 1st. It's a quarter, right? So that's right. 4 times quarter becomes 1. G of 0 is 4 to the 0. Any number raised to 0 becomes 1. Great. And next y value should be 4 because g of 1 equal to 4 to the 1st. That's 4. And next number will be 4 times as much, 16. G of 2nd g of 2 equal to 4 to the second power 16. Now if you connect those two graphs, and as you can see from left, if you put those graphs all together in the same, plot all these order pairs, right, to get this graph, and typically the overall trend here is overall trend. Since the base 4 is bigger, so after this point right here, then g of x is increasing at a much faster pace compared to f of x, increasing at much faster pace. Compared to f of x. So the bigger the base, the faster the rate changes after x value greater than 0, right? Right. This is general trend about this exponential function. That's pretty interesting phenomenon. You can use it to compare different exponential functions with the same type of base. Okay. And now the following is just summary what we're talking about so far. So following summarize the basic characteristics of exponential function y to a to the x and then y equal to a raised to negative x. So for graph of a equal to y equal to a to the x, when a is greater than 1. Domain is all real numbers from negative infinity to infinity, equivalent to all real numbers. And the range, you see, it's above x-axis. So it's from 0 all the way to, this is 0 all the way to infinity, right? So the range is 0 to infinity. Y-intercept 0, 1. There's no x-intercept because it just gets infinitely close to x-axis but never touches it. And from left to right, this is the left to right. This direction, the graph is increasing. As you can see, from left to right, it's increasing. It's going upward, right? And this way. And the x-axis is what we call a horizontal asymptote, meaning when x approaches negative infinity, a of x approaches 0. Yes. Also, it's continuous, meaning there's no hole, no gap, no break, no jump. Basically, it's continuous, meaning it's a smooth curve. Now, you can learn in a lot greater depth in calculus 1, 2, 3 when we talk about the continuities in calculus sequence. And then if you look at 1 over y equal to a raised to negative x, so you can also use the sum transformation turning into the base, it becomes 1 over a. If a is greater than 1, then 1 over a must be greater than 0, less than 1. So when the base is not a whole number, it's a decimal number. And typically this is what we call a decimal number. Then from left to right, we have an exponential decay model, right? And domain, again, is all real numbers. The range, again, it's above x-axis from 0 to infinity here. Okay. Y-intercept, as usual, is 0, 1. Okay, right here. And it's decreasing from left to right. It's going downward, right? At an uneven rate, meaning it's not a constant rate. It's not a constant rate. It's uneven rate. Also, it's continuous, meaning we're gonna see a smooth curve. For example, if you want to graph f of x equal to half, or maybe 2 raised to negative x. So if you do the transformation, it becomes half to the x power. And similarly, if you come up with the order pairs, let's say 5 order pairs, similar patterns, -2, and the y value will become 4, 2, 1, half, and a quarter. All right, so half raised to negative second power. Do one of this, and then you'll be able to see that. So f of -2 equal to 2 to negative second power. It becomes half to the second power. No, -2. So it should be 2 raised to -2. So -2. Okay. So -2. It becomes 2 to the second power. That turned out to be 4. And since base is half, meaning apply the pattern here, next y value should be half as much. That's why it becomes 2. Half as much as 2 becomes 1. Half as much of 1 becomes half. And then half of half becomes quarter, right? So you could again use the base to get all the y values. That also works. And since if you plot it, I'm gonna put it on the same graph: -2, -1, 1, 2. And you're gonna see a very similar graph, right? Let's say this is 1, 2, 3, 4. Okay. And the graph will look very similar to this, right? Okay. And the graph passes horizontal line test, meaning if you draw a horizontal line on either growth model or decay model, we will only have one intercept. You see right here, one intercept, right? On each graph. This is what we call a horizontal line. Again, draw a horizontal line, only have one intercept on each graph. So if you pass this horizontal line test, it's one-to-one function, right? That's what we learned about function in chapter 2. Yeah, since it's a function, it's one-to-one relationship. Yeah. And you can use the following one-to-one properties to solve for the exponential equations. So if we have a given exponential equation, a raised to x equal to a raised to y. Well, for these two to be equal to each other, the exponents must be equal to each other. Right? So this is what they call the one-to-one property. Exponents must be the same. If the base are the same and they are equal to each other, then exponent for both must be the same. So now let's take a look at how we derive natural base E, or natural base E, right? So first of all, natural base E is called Euler number. It's named after the mathematician who discovered this number, E. And then E is approximately equal to 2.718. E is very similar to pi. Pi is 3.1415196, right? You can have infinitely many decimal places. E is almost has similar, exact identical nature as pi. And the base is called natural base. So anything compounded continuously, meaning if anything increasing at a continuous pace or decrease at a continuously, then we can use exponential function with base e to model it. So two famous applications, population growth or population decay. Because population is increasing at a constant rate, right? Continuous rate, meaning every single moment as newborn babies. Okay, so that means it's continuous growth. And second thing is interest compounded continuously. And the graph of the function f of x equal to e to the x, it's depicted right here, right? Still, we follow all the growth model pattern. Domain is all real numbers, ranges from 0 to infinity, and then it passes through 0, 1. X-axis is the horizontal asymptote, right? Maybe just summarize that really quickly. Domain from negative infinity to infinity. Second one, range from 0 to infinity. Third one, the y-intercept 0, 1. And then fourth one, x-axis is the horizontal asymptote. And the fifth one, from left to right, is increasing. Sixth one is continuous, because e is greater than 1, right? E is greater than 1. So when the base is greater than 1, then all of this must be true. Now let's take a look at how we evaluate all these numbers, right? So x equal to -2, put into f of x equal to e to the x. So f of -2 must be e raised to -2nd power. And again, on your calculator, ti30x double ys. That is second e to the x to get base e. And -2 turn out to be 0.1353. Okay, I copy all the digits I saw from the calculator. F of -1 should be e raised to -1st power. Point 367879,441, and then f of 0.25, e raised to 0.25th power. It turned out to be 1.28, 4025, 417. And an f of -0.3, it's e raised to -0.3. And this turned out to be 0.7408, 18221. Okay, and that's how you do it by hand. And next slide is show you how to input into the calculator and get a result. Okay, right here. You can follow that. You can do it by hand, so calculator will be helpful. So just follow this instruction in the middle. You'll be able to get all the y values. as you can see from the previous slide. Also check the answer here. You should try on your own, so you know what to do. Now let's take a look at application, right? One of the most famous application, it's in the financial system in the US. Financial system. So continuous compounding is the foundation for financial system in the US, also the worldwide, right? Exponential growth is the investment earnings continuous compounded interest. Yeah. The formula for interest compounding n times per year, it's A equal to P times parenthesis 1 plus R over n raised to nt. That's a formula for compounding interest. A here is initial balance in the account. No, it's not initial balance. Should be the ending balance, right? This is a typo here. That means just balance in account, not initial balance. Should be the ending balance. I modify that in your slide. Yeah. In account, P represents principal or initial investment, initial balance or initial investment. I is the annual interest rate. It's also called API in the market. Annual percentage rate or annual percentage yield. N is the number of compounding periods per year. So if it is compounded, monthly compounded, then n equal to 12. If it is daily compounded, then n equal 365. Right, so depend on the compounding methods. And then time t is the time in years, right? T must be in years. Unit for t is years. I should go over this detailed explanation on each variable. And now let's take a look at how the interest concept comes from the Middle East back in 2,000 years ago. So it comes from Middle East. About 2,000 years ago, an interest concept. Okay. So using exponential functions, you can develop a formula, show how to continuous compounding. Suppose you invest a principal P equal to 100 at an annual interest rate of 5%, R equal to 5%, compounding once per year. If the interest is added to principal at the end of the year, then look at this. This is like the balance, right, after year one, meaning ending balance after year one, after 1 year. So typically you look at it, it's a principal, right? Principal amount. So here is $100 plus interest, since they pay 5% interest per year. So it's 5% times principal $100. So here, typically it becomes 100. If you factor out 100, it becomes 1 plus 5%. But if you look at the amount, it should be $105. But right here, let's just look at the overall pattern here. So to understand, how interest formula was compounding interest formula was developed back in 2,000 years ago. So if you factor out a P right here, right? So principal goes in the front, factor by GCF, you get 1 plus R. Okay. Look at that. This year, 1 year, power is to the first. Look at the base here, 1 plus R. It's going to be greater than 1. So this means it's exponential growth model. So that's why compounding after applying the compounding interest formula, the money is growing. the investment is growing. You're getting more money after a certain period of time. And if you look at year 2, so this is year 1, we take a year 1 right here. Look at year 2. Year 2 is based on year 1, so principal after 2 years, after year 2, should be ending balance after year 1 times 1 plus r. Again, 1 plus r is the interest, right? Similarly, it should be written as P2 equal to P1 plus P1 times r. And P1 times r, if you factor out a P1, and we get a P1 times 1 plus r, right? Factor by GCF one more time. And P1 is equal to this, P times 1 plus r from the previous step. So now, again, we get a repetitive multiplication. It's P times 1 plus r raised to second power. To the first, adding the exponents, we get 2. We look at year 2, the exponent is 2. Similarly, for year 3, P3 equal P2 plus principal after year 2 plus principal after year 2 times interest rate. And factor out P2, you get 1 plus r. And P2 equal to this. Plug in here. This is power to the second, power to the first. Adding them, you're getting 1 plus r raised to power to the third. Okay, so year 3, power to the 3. So similarly, if you generalize this to the t years, then the balance after t years should be principal times 1 plus r raised to t power. And t here represented time years. Okay. And that's how ancient mathematicians derived the interest formula back in 2,000 years ago. Okay. So to accommodate more frequent, so this is compounding yearly. So if you want to compound it quarterly, monthly, daily, I just have to come up with another, concept. N be the number of compoundings per year. So if it's compounding yearly, then n equal to 1. If you're compounding monthly, then n equal to 12. If it is compounding quarterly, n equal to 4. There are four quarters in a given year. N equal to 4. If compounding daily, then n equal to 365. Yep. All right. So again, we compounding the rate per compounding period is r over n. So right, that's why this is r over n right here. And then nt, right? The total number of compounding periods after t years should be compounding n times per year times t, nt. And when the n increases without bound, when the compounding number of compounding n increases without bound, meaning infinity, when n approaches infinity, then we have a continuous compounding case. Continuous meaning it's compounded at any given second, right? Or you basically split the time into infinitely many intervals, then we get a continuous compounding concept, meaning when n approaches infinity here. Infinitely many intervals for a given amount of time. Now let's learn how to derive the continuous compounding formula. Using some algebraic transformation. So we start with the compound interest formula, P times 1 plus R over N to the NT. Now we're gonna assume m equal to n over r. So now let's see what is r. So that means 1 over m. The reciprocal of the m becomes a reciprocal of n over r. And n over r is r over n. Okay? So if you look back in the formula, so let's just look at this part. R over n now becomes 1 over m. Right here. This becomes that. Right, 1 over m. And then let's solve for n here. N, 1 times n is n equal to r times m. Okay, so n equal to rm. All right, so that should be rm times t, right? R times n times t. Now if you just separate it really quickly, 1 plus 1 over m, we can raise exponent, right? Separate those powers. Separate m from rt, and becomes rt right here. And we're going to take a look at this particular element inside of the parentheses, right? This is where e comes from. But now this is our intermediate, result by setting m equal to n over r. Now if you look at this, when m approaches infinity, okay, then 1 plus, according to this table right here, you can also construct a table on your own. Will approach e, and this is not difficult to get, right? You basically just, let me give you an example. Let's say when m equal to 1,000,000, and then you're gonna get a 1. When m equal to 1,000,000, then plug in million here, 1 plus 1 over 1,000,000, with a 60 in the back. And you put it into the calculator. Okay, so then you get this result right here. So this is 2.718, 280, 469. And then when this number gets larger and larger, meaning when m gets larger and larger, eventually reach infinity, then this result will reach e, right? The iota number, which is 2.718, 28, right? With infinitely many decimal places. That's how the mathematician Euler discovered this number e, which is natural number. And as you can see from the previous result, p times square root square bracket 1 plus 1 over m to the m power, right, and then to the rt. And since the inner one becomes e, then the formula becomes p times e to the rt. And that's how you develop the continuous compounding formula. Continuously compounding formula. I'm gonna show you I also want to show you the real life applications, right? So if you go to Google and type in national debt, national debt real clock. You'll be able to see the US national debt, which is compounded continuously. Now if you look at it every single second, right? The national debt of US is going up. And that's exactly the notion of the continuous compounding. If you look at this national debt number, in the screen, you'll be able to see the continuous compounding. Okay. And now we have learned two formulas so far, right? N compoundings per year, this formula. And if it is continuous compounding, we use another formula with a base E. So again, both base here, 1 plus R over N, that's greater than 1. E is greater than 1, right? So both base are greater than 1, meaning it's exponential growth model. That's why if you put a certain amount of money towards your retirement account, let's say 30 years from now, you get a lot more money in the account because the money's growth exponentially. Okay. Now let's take a look at how we apply this formula to solve a real world problem, right? Let's say you invest $12,000 at an annual rate of 3%. So this is annual interest rate, 3%. This P is 12,000, that's a principal. You have $12,000 to invest. Rate is 3%. And then time t equals 5 years. You want to find the balance after 5 years. Time t equals 5 years. Okay. When interest compounded, 3 different compounding methods: compounded quarterly, monthly, and continuously. Now let's first take a look at quarterly case. So using the compounding formula, and then here principal, we know 12,000, right? Let's list out the number one more time. Rate is 3%. So if you turn into decimal, it should be 0.03. You move you insert a decimal point, move it to the left 2 units. Then we get 0.03. N is compounded quarterly, N equal to 4. And then time t equal to 5 years, 5. So now you plug in the numbers into the formula, 12,000 times 1 plus rate is 0.03 divided by 4. And then that's NT, right? NT should be 4 times 5. If you simplify, that should be 12,000. This is 1 plus 0.0075 to the 20th power. And you get this number, this result, right here. $13,934.21. If you look at it, principal is 12,000. Return on investment in 5 years. Ending balance $13,934.21 minus initial investment $12,000. The difference is the interest on the investment, also return on investment. That should be $1,934.21. Okay. That's a return on investment for the first case, quarterly compounding, right? So this is a pre-given condition. Second condition, if it's monthly compounding, again, same principle. The rate is the same, 3%, 0.03. Time t is still 5 years. But N here is slightly different. N is equal to 12 now because you're getting paid on a monthly basis, right? You're generating interest on a monthly basis, so N equal to 12. So now one more time, we just plug in on the numbers. 12,000 times 1 plus 0.03 over 12 to the NT. N is 12 times T is 5. So that should be 12,000 times 1 plus, you can evenly divide it, 0.03 by 12. Let's see what that is. Should be 0.0025. 0.03 12. 0.0025. That's exactly right. 0.0025 to the 60th power. And you're going to get this result, right? This amount. If you compare this monthly compounding to quarterly compounding, let's see which one has better return on investment. Let's look at return on investment. Ending balance $13,939.40 minus $12,000 of the initial investment. The difference is the return on investment on the interest payment, $1,939.40. If you compare to the previous one, it's slightly better, right? Not much, but slightly better. Meaning more frequent compounding give us more money on investment. Okay. Now let's look at the continuous compounding case. All right, given the same condition, P equal 12,000, still rate is 0.03%. Time T is still 5 years. That's all we need. So now let's plug into the formula 12,000 principal times E 0.03 times 5. That should be 12,000 times E to the 0.15. We put into the calculator. This is the result. $13,942.01. Again, return on the investment. So you can compare which one is the better option in terms of investment option. So using the ending balance $13,942 and then 1 cent, I mean 1 cent, right? Minus initial investment, $12,000. The difference is the return on investment. That should be $1,942.01. If you compare all three options, continuous compounding is the best because it gives you the most return on investment. Although, you know, it doesn't make big difference, but think about it. If you have millions or billions of dollars to invest, then that small difference will make a huge impact on a big investment, right? So basically, more frequent compounding, the better it is, right? The more return you generate. You are generating more return on investment. And then continuous compounding is the best options out of all compounding methods, the best option. And all the national debt, meaning the countries borrow money from each other, they pay at a continuous compound. They pay use continuous compounding method. Our national debt is also functioning in a similar way, so you can look up that online. You know, it's public information. You know how continuous compounding works in the real life. And that's pretty much it.